If I let you play the dark game, move quickly.
Yes.
So that way we can go very fast. Now keep in mind, if it slows down, we're stopping it. Because I want to make sure we're moving very quickly. I have a lot of terms and definitions to get through. Plus we gotta start drilling the periodic table still, so we got to move. Alright. Choose your darts.
Which one did I have?
I don't remember.
You had the blue ones.
You sure?
Yeah.
Is Ethan lying?
I don't
So that way he gets the good ones? I do not remember though.
I don't remember either, actually.
Okay.
Okay.
I think I got the same one I had last
I
night.
don't remember.
No,
I
it's
really
actually-
don't.
you had these.
Alright,
It
so
doesn't matter though.
we'll start with Ethan since Chris chose his colors. So, what is defined as anything that occupies space and has mass? So, the physical universe. Matter. Throw quickly.
Two throws.
Remember, 2 throws. We'll say from
Whoa.
the edge of the desk right here. Oh, let me move the camera up.
Are we recording?
Yep. Sorry, Jamie.
I quit.
Oh, there you go. You can stare over there.
One! Alright. If
Alright.
this don't stick today, I'm gonna throw something.
What is it on?
7. It's closer to 7. Oh, Chris is in the shop. Sorry, Jamie. Quentin. You should
Hey! Wait, right
stare
here.
at the ceiling.
No, it's your boy.
We'll say the front edge of this desk. So I can get a little bit closer. What are you doing? I didn't ask you a question.
What? Oh yeah, you're right.
Hey, Craig. Good.
What is the energy of motion?
We'll start with.
Energy of motion. It starts with K. Okay. Through. Hey.
4. Trash.
Alright, what is an indirect measurement of the particle's average kinetic energy?
What?
Indirect measurement of the particle's average kinetic energy. So you can't take like a direct measurement of how much energy they have. So what do we use to take an indirect measurement?
This is how
T.
PCs.
Get that. What? Say it one more time.
An indirect measurement of the particle's average kinetic energy.
I don't know.
Alright. Temperature. Yes. 2 thirds. Hey! At least you're sticking today. So that's good. Hey.
Is that on 15?
It's 15.
15. Yes, sir.
Alright. What is the state of matter that has the lowest kinetic energy?
Solid.
Solid. Come through.
Oh, no.
Okay. That's
It's
all.
on 15, but if it falls. That was so vicious.
It really is these.
Alright, what is the state of matter of the 4 total states of matter? Which one has the most kinetic energy? Plasma. Come through.
See, I told you it's not just these.
Oh, I'm sorry. Alright, what is the transition point if you're going from a gas to a no, that would be too confusing. We'll talk about that one later. What if you're going from a solid to a liquid? What's the transition point?
Solid to a liquid.
Solid to a liquid.
Melting point.
Yep.
Is the next question going to be the next one?
Yes.
What was it for?
Wait, let me give my definition. I'm sorry.
It is these.
Here, take.
No.
Take
No,
out the
you
blue
can't
ones.
because it's Corona, and so since you've touched them now, we'll try to divide them up to where I don't
Honestly, I never
think
tried to
that-
help you.
These are horrible.
I'm sorry. I don't know why. Like I bought them at the exact same time, and I treat them the exact way. I don't know
It's
what
because
caused
the
them.
magnets on the end are, some of them are chipping around.
Well, that's because people throw them too hard and they chip them.
Or they're really bad and they hit the board.
Yeah, that happened too. I had marks like the magnets were like coming apart, and if you look at the other side, there's like skid marks where people have thrown them so hard on my magnets. Okay, so what's the transition point between a liquid and a gas? One, hey, that's 25. Unless you knock it down, so be careful. Yay,
They
good
could have
job.
up there on purpose.
Yeah, I'll try to remember to put the red ones
It's
away,
all right.
then we'll just divide up the blues next time. Alright, what is what state of matter is it whenever you have the molecules, they are attracted to each other, but they can move around each other still. They don't have enough energy to break away from each other. It is his turn.
Wait, is it like a
Like solid, liquid, gas, or plasma. So they're moving,
Which
but they're
one
not.
is it?
Yeah,
Liquid?
liquid.
I was thinking like.
I still do these stuff. Kobe.
Hey, it's stuck.
Kobe.
Bummer.
Just
All
put it
right,
somewhere.
which one is it? Whenever you have whenever you have the particles of the substance, they have enough energy to break away from each other now. Solid, liquid, or gas, or plasma. Yes, correct. Okay, well it's at 11 right now.
I'd right now.
Hey, so 11, and that.
Is that 18?
Oh my god.
Or 25.
It is exactly in between, so you can keep the 4 or you throw.
Why
Yeah,
keep
but
the
you don't
lesson?
wanna- you don't
Like,
wanna
why
knock
can't
down
that be
11?
like 20 and 5?
Kobe.
Hey, 14!
That's half one on. Okay.
What?
It's in barely one.
414?
Yeah.
Since it's touching it, I'll take it.
Bruh.
Alright, so what is the state of matter then whenever they have so much energy that they break apart into ions? That's plasma. At least
No,
it's
they might
sticky. Hey,
Oh!
22. Alright, what
21.
is,
Is there one up there?
alright, what do you call the smallest particles we can have and have them still be, and still remain like part of an element? So like you chop down a piece of copper smaller, 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 and it's still
69?
copper. Atom.
You're 69.
What?
Why are you cheating? Stop worrying about his points.
No, you don't. Hey, Press, stop being horrible.
Alright, what is, alright, what do you call a group of 2 or more atoms that are just linked together by chemical bonds? Could be
Element.
same, could be different.
Element?
A group of 2 or more atoms linked together.
Say it again?
A group of 2 or more atoms linked together. Could be the same element, could be different elements.
To start with.
M. Okay. Molecules.
Oh, that's
So if
what I
I
was
throw this,
thinking.
if I throw this and it hits your what stick?
Huh?
If I throw this and it hits your what stick?
Probably.
Yo, you got fruit.
13.
Okay, it's in between.
Or 9.
Yeah, it's 9. Because it's in between them. 9 and 5. Alright, what is it called whenever you have 2 or more different atoms put together? Now specifically, what do we call that type of molecule?
What kind of molecule is it?
Yeah, if it's 2 or more different atoms.
Start with.
C.
I know this. White molecule, is that what it is?
What?
Something molecule?
Nope, it's like water is this. Because it's 2 or more different atoms put together.
It's right there.
Yeah, it's okay.
Starts with C.
So C. Alright, compound.
That's what it was.
Compound. I know, it's just Thursday. Compound.
You did.
Alright, name a diatomic element. You're talking about how there's 7 of these in your book that you need to know. There's an easier way to memorize them if you use
Water.
your table. A diatomic element.
Ion.
Element.
I know.
Pick one.
Oxygen.
You're gonna pick oxygen?
Chlorine.
You're gonna pick chlorine? You sure?
Yeah.
Yes, chlorine is correct. Because remember, diatomic one is one that likes to exist with a partner, so it's nitrogen through iodine or hydrogen. At least you got 3.
It hit right here and fell off.
It's like Patrick. I go wrong.
Okay.
Go
Alright.
on.
Don't be distracted. Let's
wrong.
see. Alright. What do you call a substance that's composed of the same type of matter throughout? Could be a mixture that's all the same, or it could be like a solid gold bar. H. H. You should describe it as the same throughout. You might remember this from biology. It's the same prefix. Like we use in biology for this thing. Alright, Ethan?
Say one more time.
What do you call a substance that's composed of the same matter throughout? It's all the same. So it could be like a mixture that's made of all the same stuff, or it could be a compound, like water, where it's just water all the way through it.
It means same.
Yep.
Homogeneous.
Homogeneous or homogeneous. Sorry, Ethan.
What is that?
That's a 2.
Of course it is.
There's a little metal part.
Chris gets all the big numbers, but I get the small
It's
numbers.
okay, Ethan. It'll be okay. What do you call the substance that is made of different material throughout?
So is it homogeneous? So is it homogeneous?
Okay, you're just pronouncing it weird because heterogeneous. So hetero means different. It means it's stuff.
You can. Okay.
Or manual. Alright, what do you call a homogeneous part of the system that's in contact with but physically distinct from other parts of the system? This is one reason why if you have your salad dressing, it'll split into those different sections. What do you call those different sections? Don't break my magnet.
The different sections.
Yeah, what do you call it to where it's a homogeneous
start
part? P.
I looked over this, but now I don't remember it.
Alright,
What's the question again?
make sure you're paying attention to play with my magnet. What do you call homogeneous parts of a system? It's in contact with but physically distinct. So like water and oil separate into oil on top and water on the bottom. So what do we call that?
Plutonium.
Nope. Phase. So make a note of phase. Is a homogeneous part of the system that's in contact with but physically distinct from other parts. This is why oil will stay on top of water.
Is it spelled F-A-Z-E or F-H?
What's the compound again?
P-H-A-S-E.
No.
What's the compound again?
2 different atoms put together.
And then what's an element?
An element is a substance that can be broken down into an atom and still be the same type of substance. So like copper gets smaller and smaller and smaller, so eventually you have an atom of
It's
copper.
still compound.
But I think it's technically easy because it was phase for him. Alright, who came up with the atomic theory?
John Ball.
Good job.
Dawn East.
That's how they remembered it last year. It was like Dalton's favorite question. He was excited.
I mean, you're trying to Kobe in it, man.
Alright, gotta go
It's going
over
straight down.
parts of the periodic table. Keep in mind, this quiz will be next week sometime. I don't know for sure. It might be Tuesday or Wednesday. So make sure you're setting to stay on top of it because you don't want to get caught off guard. So what is this one?
Is that me?
Oh, I'm
Yes, it's you.
Gotta bring it down a little bit so it is. You can see it.
Can I go back to
Oh,
the
you can
can I go
tell.
back to the review page that we had yesterday?
The review pic- Nope, you should know it today. This is one of the ones we had yesterday. Remember?
Is it,
HG.
does it look like, is there an HG in it?
Spits up the old name.
Iodine.
Nope. Ethan?
Start with this.
Nope.
Mercury.
Mercury. Good job. I'm gonna slide it back up. I'll put it here. I think. Nope. You can still see people.
He got this other dart. I literally didn't touch it.
You sure?
Yeah.
You may give it to him then.
Ethan, come grab this dart.
Alright. What is this one? Good job. Trying to make sure they can see it without seeing you. I don't want to move it over and over again. Sorry. That happened to Dalton. It literally went down the whole thing last year. And it was one of those. I'm just very, very sorry. Oh. Alright. What
Give
is
me my
this
dart
one? Yes. Sure.
Ascending.
No, that's not close. That's not close.
I can't give that.
Acetone.
Is that really
Ardentic.
What?
Ardentic.
No.
You're getting closer, but no.
Arsenic.
Arsenic. Arsenic.
Like an arsonist, like they burn down houses?
But I mean, don't like. I don't know if that's
Salt?
helpful for AS, but it helps you whatever.
Salt. 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 Salt.
3. Alright, we're gonna have to do maybe just 2 more apiece because I gotta go. Next time at the end, we'll come back to it. But make sure you're setting the periodic table. Alright,
Good one.
Ethan.
Fluorine.
Good job.
Sounds like a name from like Louisiana in 1800s for him.
He does. Woo! Alright. RV.
Virginia.
Which one?
Virginia.
Rubidium.
Rubidium.
Hey. Ooh, let me look.
That's 3.
That's cool. That's me know.
That's 3.
No. Do you get 3 or we do? Okay.
Plus you get a 50. Shoot your
Alright, last one, Ethan, for you.
An A.
Yep.
Does it really start with an N?
Nope.
Does it?
Nope.
N A is
Not available.
not available.
Don't give him unhelpful. He's gonna remember that on the quiz and write not available and then you're off. Don't give unhelpful hints.
N A is. Yeah, you can
Okay.
Well, I get a different card.
No, you get this card. You get
I
one.
get another question after that because you said you get 2 questions. I've only had 1 question.
Yeah, you say 2 questions.
He gets one and then you get one, but if you don't know, it goes back to Ethan.
There's no N.
In A. There's no in A. Like there's no. It doesn't start with an N. Couple seconds. We gotta go. Running out of time.
Is it? Oh. Is it sodium? Sodium. Sodium.
Sodium.
Bruh!
Woo! I'm like, stop going. You're having.
Sodium chloride.
50. That hit
Alright.
for 25.
You technically stole Ethan, so we'll do one more card in general and then we'll stop for it. Alright, Ethan.
Coin!
Yep.
Chlorine.
Karen.
McLaurin. Karen.
Karen!
Sorry, Ethan.
That's the pressure.
Sorry, Ethan.
I
Alright,
didn't get it.
I'm pretty sure we know who won, so go ahead and add up your points just in case.
I'm not gonna have my.
Okay, so you just admit defeat at this point.
Yep.
I'm sorry. I'll try to divide up the blues to where someone gets 1 red and 1 blue.
I had 95.
Oh, well, good job. Alright, we'll do it tomorrow. If we do it, we'll probably not tomorrow.
You get on my
Maybe
candy.
next week. We'll do
Yes!
it where we each get 1 blue and 1 red, so that way you both get a handicap for it.
Alright, let me look over real quick.
Alright, go ahead and take out your textbooks and turn over to page 22.
What?
You don't have the quiz today, but if it's not today, what does that mean? Tomorrow. So study and be ready. So if you were struggling with compounds and elements and homogeneous and molecules and gas and boiling points and kinetic energy, you should know it. Study. We're going to finish up some material today as well, so make sure you study today's material, the terms, so you'll be ready for stuff tomorrow. Alright, wait, you have a question?
No, I was saying I might actually take the
You gonna what?
I'm gonna take the
Okay,
I
go.
said originally I was gonna get down on that.
Alright, turn over to page 22. So, the atomic theory, we read through these super briefly at the end of the period, last class period, and we just talked through them, but I need to go over and actually talk through them with you now. Alright, let's read through them again. I know we read through them super quick, but let's read through them and actually think about them as opposed to just speed reading. Alright, Ethan, we'll start with you.
Number 1.
Number 1.
Every element consists of tiny indifferent bits, indivisible, indestructible particles.
Good job. Alright, is that true today from what we know?
Yes.
Is it?
No.
Nope. So today we know that we can take atoms and break them apart into smaller pieces called protons and neutrons, and we can even break those down. But back in the day for John Dalton, he didn't know that, so he thought that they were just made up of these tiny, indestructible little spheres, basically. So that part's not true. Alright, second one. Chris.
All the atoms of a particular element have the same size mass.
Alright, so is that true today?
Like,
No, it's not. We actually know that some of them are heavier than the other. We'll talk about why. It has to do with the number of neutrons that they have. We call them isotopes. But again, he didn't know that at the time, so this was his best guess. Alright, number 3, Ethan.
Difference in properties of elements result from differences in the atoms of the element.
Alright, is that true today?
Yes.
Yes, it is. This is one reason why carbon, okay, it's still carbon, but depending on how you hook it up together, you can get a diamond or you can get coal. So, the differences in properties of the elements result in the differences in the atoms. In some cases, it might be an entire different atom. In some cases, it might be how they're hooked together. Alright, number 4. Chris.
the atoms of the element combined in the compound are combined in a different ratio.
Definite ratio. So, is that true today? Yep, it still is. Alright, and the last one, number 5. Ethan, let's go back to you.
A chemical reaction is the result of rearrangement of combination. separation of that.
Alright, is that true today?
Yes.
Yes, it is. This is one reason why, whenever you have a chemical reaction, you get an entire new substance. You don't have the same substance anymore. So your book tells you in that second paragraph about it that, okay, the first two parts of Dalton's theory aren't correct, but it was a good guess at the time based on what he knows, but we know today, okay, this isn't quite right. But because of Dalton's theory, we have two laws that have come about that we say, okay, this seems to be true as far as we know, that these two laws that came from Dalton's atomic theory seem to be right. So make a note of these laws. So law of definite composition, sometimes it's also called the law of constant composition. This states that the ratio of the masses of the element in a given compound are always the same. Now, think about it with water. Alright, what is water made of? Anyone know? We know we've talked about water a whole lot.
Hydrogen and oxygen.
Hydrogen and oxygen. Do you know how many hydrogens?
2.
2. So it's H2O. Now, it's not the number of atoms, it's the masses of each element in a given compound are always the same. So, loosely, you can figure it out from the periodic table, but we're not going to worry about that right now because you'll learn that later on. But loosely, water is 88% oxygen by mass, by how much oxygen weighs. Since hydrogen is so much smaller, hydrogen only accounts for 11.2% of the mass of an individual water molecule. Now, you might think, well, hang on, there's 2 hydrogens. Yes, but hydrogen is so much smaller that by weight-wise or mass-wise, it only accounts for about 11%. Oxygen counts for the other 88, I forgot my 0.8%. So, mass-wise, oxygen is a lot heavier for it. So, your book points out, and scientists have noticed as well, that it doesn't matter where the water comes from. If you have water, it will have 11% of it will be hydrogen by mass. 88% or 89 if you want to round up percent of it will be oxygen by mass. Doesn't matter if you get it from an ocean, if you get it from the top of a mountain, if you get it from a whole other planet. If it's going to be water, it'll be about 11% hydrogen and about 89% oxygen. Over and over and over. If that ratio is not right, if you do not have 11% hydrogen and 89% oxygen, you do not have water. You have some other chemical or some other substance. So also comes scientists say that, okay, this is the law of constant composition. You will always have this composition of the masses of water, and then every other substance follows that same rule with the idea that the ratio of the mass of an element in a given compound are always the same. Alright, anyone have any questions about this idea? The second one is a little bit more confusing, the law of multiple proportions. This states that when you have 2 elements that can combine to form more than one compound, the masses of one element that combine with a fixed amount of the other element are in a ratio of small whole numbers. Now remember, what is a compound, Ethan?
Is something what you have to be different from each other. The elements.
Just say it one more time, I just couldn't hear you very well.
I believe it. Where's a compound?
Yep.
Substance that can be decomposed by chemical means as a simple substances.
That sounds like an element. Okay, a compound is 2 or more.
That's what the definition for compound.
Read it one more time is?
A substance such as water that can be decomposed by chemical means or substances is a compound.
Okay, that's what you're saying. I thought you were saying and giving a definition with the atoms breaking apart to a smaller and smaller substance. Okay, so yes, a compound is a substance that can be decomposed into a similar substance or 2 or more different atoms. Just make a note for the definition for it. But yeah, either definition works for it. So for this one, it states whenever you have 2 elements that combine to form more than one compound, the masses of one element that combine to fixed amount of the element are in a ratio of small whole numbers. Alright, so you can have oxygen and hydrogen combined in one way to get water. You can also have them combined in different ways. This is not the only way how hydrogen and oxygen combine together. You can also get them to combine H2O2. Anyone know what this substance is commonly called? We have a name for this.
Hydrogen water.
Nope.
Hydrogen oxide.
Nope. You probably have this in your medicine cabinet at home.
Tylenol.
Nope. You dump it on cuts and it fizzes.
Marijuana.
No, do not dump marijuana on cuts, first of all. Ugh. What did you say?
Cocaine.
No, don't do that either.
It's
No
Heroin.
illegal drugs in your cabinet.
it's hydrogen chloride, not chloride. It's
Don't put hydrogen chloride on cut.
dead.
Don't do that.
Carbon dead.
You know what? It's an acid. It'll eat through you.
What's a peroxide?
Hydrogen peroxide. So yes, this is the one that fizzes. Now keep in mind, you might think, well, it's just another oxygen. No, this one you need for life. You need water, H2O, every single day. You drink hydrogen peroxide, you're going to be dead pretty soon. So that's part of the reason why just that one different atom creates a whole different substance. It's not like it's just extra oxygen water. No, entirely different thing. But that's what your book is talking about with the law of multiple proportions. The ratios of the masses, they combine in small whole numbers. Like basically the ratio of the weight to the hydrogen to the weight of the oxygen in the water is about a 1-to-2 ratio. So because of that, 1 to 8. Because for the masses, for every mass of hydrogen, the oxygen is about 8 times as greater. So that's one reason why it's about 11% to 89% if you were rounding up previously based off the masses. The total mass of the hydrogen to the total mass of the oxygen in water is about a 1 to 8 ratio. And that's the idea behind that one. Now, for this one, for hydrogen peroxide, it's about a 1 to 16. Again, because it basically doubles because there's 2 oxygens for it. So it's the small whole number ratios in between them. So because of that, the weights of the oxygen and that will combine with hydrogen are a ratio of 8 to 16 or 1 to 2. It's a small whole number ratio. And so that's where scientists are getting their numbers for this law of multiple proportions. Now this makes sense because since these substances, are made up of atoms, and atoms hook up together in small whole numbers. So 2 atoms to every oxygen, or 2 hydrogens to every 2 oxygens in hydrogen peroxide. Since they're made up of small whole numbers, the small whole number ratios, like for this one, it's a 1 to 2 ratio or a small whole number. And so that's what scientists are saying, okay, and that makes sense because they combine together in small whole numbers. Here I give you another example with carbon and oxygen. We looked at these two yesterday. All right, so what is this substance? Anyone remember from yesterday?
Carbon dioxide.
Carbon dioxide?
Carbon monoxide.
Carbon monoxide, this is from combustion, and this one is what then? Carbon dioxide. So your book points out weight-wise, the weight in a carbon monoxide, the ratio of the weight to the ratio of the carbon to the oxygen is about a 1 to 1 1/3 weight-wise between it. For down here, it's between a 1 to about 2 2/3 ratio. Because again, oxygen is so much larger than the carbon. So again, it's a small whole number ratio between them. So that's just what your book's pointing out. Some students have a little bit of a harder concept, but it has to do with the ratio comparing one substance to another substance over how they combine. All right, anyone have any questions about the law of multiple proportions? All right, do note those 2 laws, do note what they mean for them. All right, moving on then. So properties and changes of matter. There are 2 different types of properties you can have with a substance. So to make it up for it, one type of matter, it can be described or identified or distinguished from another by its properties or by its characteristics. If you had to describe water, how would you describe it? Ethan?
Wet.
You mean not Ethan? All right, how would you describe it, Ethan?
Wet.
Wet. How else would you describe it, Chris?
Dry.
For water.
Is
Water
water wet
wet?
or is water dry?
Water is wet.
It makes things wet if you want to get technical. But if you had to describe water to someone, how would you describe it?
Tasteless.
Okay, yeah. So it might be tasteless. That's how a lot of people describe it as well for it. Where is my slide? How does it go?
Clear.
Now it's gone. Yeah, clear. Oh well, I don't have that slide anymore. Apparently.
Acidity.
So clear, you might describe it as tasteless, you might describe it as typically it's kind of a colder temperature for it. So those are its properties. Now some properties describe them as physical appearance. So we call these physical properties because it describes them physically. So if you're describing someone's physical appearance, how would you typically describe them? Ethan?
Ugly.
Oh my, okay, you could. But you could describe them typically by hair color, eye color, skin color, height. You can do it something else, what was it?
Thick.
You can do that, be sure to raise your hand though before you just talk out so that I don't get distracted by it. So those are some of the examples for it. Alright, so your book points out solubility, density, hardness, taste. Now you should go around tasting
Taste?
things. Taste. Now for some
You
people,
want taste?
wait, raise your hand. Taste, you know, we're not talking about properties, not for people. We're talking about substance. So, like color, odor, density, hardness, solubility, taste, state, melting point, boiling point, those are all properties of a substance. So, if you're looking at a chemical, some of them taste chemicals. I've moved on. Make sure you keep up, Chris. We're moving on to describing people. Alright, other properties, they describe how matter reacts to changes with another chemically different substances. We call these chemical properties. A chemical property is whenever you have one substance changes into an entirely different substance. So, chemical properties can only be determined by chemical reactions, and a lot of cases you don't know how it will react until you mix two things together. Alright, so physical changes. Changes in the physical appearance of matter do not change the identity of a substance. So, if I were to take a 3x5 card, no, I have to spare one to and I were to take, I were to take my 3x5 card and I were to color all over it with a crayon, would it change what my piece of paper is made of, Ethan?
No.
No, it might have some dye on it, but it's still paper. It's not changing. Just changing up the color doesn't change the properties of it. What if I were to tear it into pieces? Would it change would it change my 3x5 card what it's made of? No. What if I were to tear it into itty bitty little pieces? What if I were to crumple up and change its shape? Would it change anything? No, so all those are physical changes. What if I were to light my paper on fire?
Technically, no.
What does it change? So it's still paper? If I were to light it on fire?
Yeah, it's still paper until it disintegrates.
So if I were to light it on fire and it's burning, so it's a chemical reaction, what is my paper turning into?
Ash.
Yeah, so that would be a chemical reaction. Now, as my fire slowly goes through my paper, that yes, until the fire burns it up and takes those chemical bonds and makes energy and light and heat from it, it's still paper. But the second the fire changes it into something else, now it's ashes or dust or just kind of like city stuff basically at that point. Wait, remember, we can't keep talking out. Remember to raise your hand. Same thing for you too. You raise your hand. Alright, so that's the example of like physical changes. So your book points out going from a solid to a liquid, is that a chemical change, Ethan?
No.
No, because it's still like water. If you go from ice to liquid water, it's still water. You're still H2O. What if I were to take my desk and melt it from the metal portion into a liquid portion of it? Would it still be the same substance? Yeah, so is that physical change or chemical change?
Physical.
Physical, yeah, so it's a physical change. So just make a note though, your book points out that just because it's changing how it looks in some cases doesn't mean it's changing the entire identity of substance. What if I were to take sugar and dissolve it in water? Would that be a chemical change or a physical change?
Just, chemical.
Is my sugar changing into an entire new substance?
Yes.
What's changing into?
Sugar water.
So is sugar and the water chemically combined?
It disintegrates.
So, if I were to have a sugar molecule, I have to think of the glucose one. So, we'll just do the glucose. So, C6H12O6. We'll just do glucose for sugar. Technically, fructose or table sugar is slightly different, but we'll just keep this one for right now. So, if I were to take this sugar molecule and stick it with water with H2O, the water molecule and my sugar molecule combine together to form a whole new substance. Nope, they don't. So, what are they doing?
Physically changing.
What you're thinking of is dissolving. So that's the term you're thinking of. So think of it this way. Could I separate the sugar and the water back out if I wanted to?
No.
I couldn't?
How?
You could evaporate the water. And that would leave the sugar behind. So think of it.
Bear Grylls.
What?
It's like Bear Grylls. Like I can disintegrate the salt water and turn it into water.
Well, yeah, no, that's the reason. Unless how you purify salt water if you're stuck on a desert island, you can build a special way to where the water evaporates and you can retake it back down and keep it that way. What? If you have a way to capture the boiling salt water, which typically, if you're on a desert island, you might not have a way to boil the water. Look, maybe you typically just the heat or the sun to evaporate it. But if you have a method to do that, then yes. But you have to have a way to catch the evaporated water, so that way you can keep that as a purified version. We don't have time to talk about water. We don't have the time to like go through all of it. But yeah, that's one reason you go ahead and separate out. So if you can separate them out again, like for salt water or sugar water, they're not chemically combined together. Now I know you can't really see them anymore, but they're still just mixed together. So what do you call a mixture though that is almost the same, that looks the same all throughout it?
Homogeneous.
Homogeneous. So it's a homogeneous mixture, so it does look the same, but you can still separate them out. So this isn't a chemical change, it's just a physical mixture at that point. Alright, your book points out physical changes may often be reversed by a physical process, so like how we were talking about how you can separate them out by a physical process. What if I were to mix iron and sulfur together, little bitty pieces? They look about the exact same. Well, let's see, how would I separate them back out? Anyone know? based on the properties of iron, you might could figure this out.
Very carefully.
How would you separate them? Because they're itty bitty grains.
So iron, they're itty bitty grains, they're microscopic.
Okay, let's say they look like dust, so you can still see them, but
There's
it would
no
be
color
extremely
change.
hard. Sulfur's technically more of like a yellow color if you were to ground up pure sulfur and pure iron, so they're more of like a reddish color and reddish blackish color and like yellowish color. But they're so finely together, it's like sand particles
Couldn't
mixed
you
together.
like use a magnet?
Yes, actually, and that's what your book points out as well. That yes, because it's iron, you can use a magnet because you know iron it is attracted or magnetism. Sulfur is not. So even if you were to mix those two grains together, if you were to take a magnet, you would get all the little iron films separated out. That's the reason why you might have played with the toys growing up that has like the face on it with like the little iron dust on it, and you can make them have like a mustache and beard and all that on it. That's the reason why it works, because it's little bitty iron dust on the inside, basically. Alright. Alright, anyone have any questions about that? With
Nope.
physical changes. Alright, chemical changes. Chemicals is whenever you're having a substance becomes an entirely different substance. So if I were to light my paper on fire and it turns to ash, it is now an entirely different substance. I'm not going to do this today because I don't like making smoke in my room. So, just make a note though that if you were to light it on fire, it is now chemically changed entirely. Your book points out and talks about sodium chloride in particular. So, sodium chloride. Now remember, we talked about this yesterday or 2 days ago. What is this substance normally?
Sodium.
Okay, yeah, so there's a common name for sodium chloride.
Salt.
Salt. Now, normal table salt does not react. We talked about this, how sodium is highly reactive, and your book talks about this as well. It's extremely reactive with water. If you were to take pure sodium, stick it in your mouth, and go to the hospital. Chlorine. Anyone know what pure chlorine used to be used as?
Pool lava. Like pool here.
Okay, that is a chlorite. It's an ion, and it's a cleaner ion. So pure chlorine gas. You
Oh.
know what we used to use it for? Dangerously.
World War II.
World War One.
World
And
War
then,
One.
yeah, and they would.
Gas
The
mask.
Jews.
They would use. Sorry, what?
I thought it was the Jews.
They might have used them in the Holocaust, but basically it's a poisonous gas. You would die. Yeah, basically. And so that's part of the reason why that gas, pure chlorine gas, is super dangerous. So these two substances by themselves in their pure form, highly dangerous. One of them will kill you if you breathe it. The other one, if you stick it in your mouth or stick it on water, or even with your sweat, it will explode basically. So these two, both of them super dangerous. Together though, makes them both stable, and now together, you can eat this. You eat this probably every single day. If you live in America, you probably eat it multiple times a day because so many preservatives are in your food for it. So because of that, you get it a bunch, and your body is perfectly fine with it. Okay, is there a question though?
Yeah.
Okay.
Why do you think someone thought to let's put these two deadly chemicals together and eat it?
Alright, where do we get salt from? There's a couple different ways to get it, but where's like a really common way to find salt?
Ocean.
Yeah. So I mean, they naturally want to be together. So sodium and chlorine, because of how they want to react, it has to do with the number of valence electrons or how many electrons they have in that outermost shell. They want to react and be stable. Sodium wants to give up one electron. We're gonna talk about this way later, so don't worry about it right now. But it wants to give up one electron so bad that if you introduce it to basically any other substance like water, it shoves the electron on it, and that's what becomes basically so explosive because it wants to do it right that second. Chlorine only needs one valence electron to be happy and satisfied. Again, don't worry about why, but it only needs one more. So anything you introduce to it, basically it says taking it. I need one valence electron. I'm taking it right now. So, but once you put them together, sodium loses its one electron, chlorine gains it, and now.
Like you thought to eat it.
we're fine.
Like why would you think to eat it?
I mean, I guess they got it from salt water. And again, if you have salt water evaporate, it leaves the gritty salt behind. And so they tasted it and probably realized, this would taste good in my meat or on my food. So I mean, the original people have known about salt for a very long time. Since ancient times. Probably since Adam and Eve, honestly.
And they
Probably
use
whenever
it to preserve.
Yeah, they knew that it was a cleansing agent. They knew that it would, like that's from the Bible references, using it as salt in the wound. They knew it cleans wounds. No, it's not fun. This is one reason why you jump in the ocean with cuts on, or if you know, or if you didn't know you had a cut. You know, very quickly once you get in the ocean, you know every single mark on your body, every single cut and open scrape. Even if you didn't know it previously, you know now, because the ocean is cleaning you. So it'll help you heal faster. It's just not fun. It's also why you don't open your eyes underwater in the ocean. It burns. Okay, is this a quick story?
Yeah.
It probably looks like a story.
It
Okay,
is.
go fast. And then
I
I'll go
had a
to
long cut on my foot and I didn't know.
Yep.
And I hopped into the ocean like a year ago.
Yeah. The ocean lets you know very quickly. Okay, fast story.
It's not story.
Okay.
So you know how in movies they pour alcohol, like actual drinking
Mhm.
alcohol in movies? What is it in alcohol that cleans you?
It can help be a cleansing agent
What's
as
like the
well.
carbonized?
I'm trying to think which part would do it. It's probably the OH part of it that's cleaning and reacting. Off the top of my head, I don't know because it's not something to where that's that shouldn't be like a standard of you have a cut, let's dump alcohol on it. That should not be your
It's like
standard.
in
go-to.
zombie movies and like Walking Dead.
Yeah, I've seen those for it's because it does work as a cleansing agent. I don't know the full-on chemical reaction for it. I'm assuming it's the OH part, but again, I haven't looked to see from the medicinal purposes of which specific part of an alcohol group does the cleansing. That's why rubbing alcohol, you can also do it. It's a type of alcohol group, so it's one of those to where you dump it on your cut and it still hurts. It's still not fun, but it's cleansing it. Alright, but good questions of that. So let's keep going though for it. So the other examples of chemical changes could be like rusting of iron. This is one reason why if you have like iron or exposed metal on your bike and you get water on it, it changes into that red rust. The rust is now chemically different than what your metal was. That's the reason why you can flake off the rust off your bike, and it basically makes a little dent in your bicycle because that metal is now chemically changed. It's also not safe to ride anymore. Like if you have a rusty chain on your bike, you don't want to keep using it. Someone's like sawing something. You don't want to keep using it because your chain might really disintegrate depending on how much rust has gone through your chain. It's something you gotta be careful from it. Now, a lot of people assume when you get tetanus from rusty nails, technically, it's not the rusty nail part. Anyone remember what actually causes tetanus from biology last year? Since both of you had biology.
Bacteria.
Honestly, the bacteria.
Good job. So it's because the type of tetanus, the type of bacteria that causes tetanus, it has to live in a very small area where there's no oxygen. So if you have a deep, narrow cut, like stepping on a nail, the bacteria can get up in that and live and then cause the infection. So a lot of people assume rusty nails cause tetanus. Technically, no. It's the long puncture wound that the bacteria can live in. But yes, if you step on a rusty nail, it'll create that opening and then you can have it live in there. Alright, Yuba points out other examples of it are digestion of food because your body is physically taking light blue glucose and breaking it apart into energy, so it's changing the substance, that's a chemical reaction. Burning of gasoline, cooking of eggs, burning of a match, grilling of steaks. Now, that's the reason why you have to cook some food fully all the way, is because you're chemically changing how the proteins are bonded to each other. That's why you want to cook eggs that the white part, or the clearish part, typically is how it starts off, it changes into kind of like a white puffy texture because it's chemically changing on the inside for it. Typically for chemical processes, in most of these cases, you can't really go backwards. Some of them, you can chemically make them go in reverse. We'll talk about that in a later chapter, I think chapter 14. Chemical changes can only be reversed by other chemical changes. In some cases, you can force them to go backwards. In some cases, like grilling of steaks, can you ungrill a steak?
Yes.
How, Ethan?
Couldn't freeze it.
Ethan, that's not going to ungrill the
Spray on
steak.
shoes.
You're going to cool it down, but you can't uncook it. So same idea with baking a cake. Once you bake the cake, you can't unbake it and re-separate it back out into its original components. You might can chop up into pieces, but you can't undo the chemical reaction. So some things you can't go backwards, but some chemical reactions you can. Alright, there's a number of signs you want to look for to see, okay, have I had a chemical reaction? You should memorize this list at the bottom of the page. Just saying. So a number of observations can be made that will suggest that a chemical change has occurred. Alright, what's that first one, Chris? On page 24. Bottom of page 2, 4 bullet points.
Page. Formation of a gas.
Good job. So if you mix two things together and a gas comes out of it, first of all, you should probably run. And then second of all, you know a chemical change has occurred. There's one reason why you don't want to mix ammonium and,
Ammonia?
yeah, ammonia and what's the other one? Bleach, chlorine together.
Ammonia?
What?
Is it ammonia or ammonia?
It's
Ammonia and ammonium are two very similar things. It's whatever's in Windex. I think it's ammonia. That
I
one.
thought it was ammonia.
I don't know off the top of my head. Like I said, it's whatever's in Windex and bleach. You don't want to mix them together because it creates a gas. Breathing it in a small amount should probably be okay, but you don't want to breathe it for a long period of time. It'll hurt you. So the reason why your mom might have yelled at you if you were cleaning the windows at the same time she was using bleach somewhere in the bathroom because she's telling you to stop mixing them together. That's the reason why it's because it can be dangerous.
So
Very quick question.
Ammonia, isn't that a household, like in cleaner?
It's in cleaner. I can't remember if it's ammonia or ammonium.
It's
It's
super
two.
small.
It's two different forms of basically the same thing. So check the index bottle, it'll say if it has ammonia or ammonia.
So if I
That's why
put those together, it explodes.
it won't explode, but it makes a toxic gas, so don't breathe it for too long. Alright, we're gonna go on to the next one though. Formation of a, oh, it's Ethan's turn to read.
Formation of a precipitate.
Good job, so that's an insoluble substance. I'm sorry. Alright, so if you mix two liquids together and you see it turn into brown stuff at the bottom of your beaker, sometimes they will chemically combine it into a solid. So if it does that, you know, chemical change, I have a new substance. Alright, next one.
Liberation or absorption of heat, light, or some other form of energy.
So if you mix two things together and heat, light, and energy comes off it, so basically it explodes, you know you have a chemical reaction. It's releasing a ton of energy. That's the reason why if you light paper on fire, it burns, it's releasing heat, it's releasing iron, it's releasing light, and it's basically changing into a new type of ash, basically at that point.
We should
It
test
does.
it.
It'll make smoke in the room, and I don't
Maybe
want
we'll
to
wait.
What?
Can you-
It'll stay in here for a while, and I have another class right after this. So maybe on a different day we can try to do it, but I have not prepared
Or maybe in
mentally.
Friday, still young.
No. Alright, so just make a note that liberation or absorption of heat, light, similar form of energy. You can light people at your own house on fire. That's something you have to do in chemistry class.
That's a good way to get grounded.
That sounds like it might be.
It's a good
Alright, a
way.
distinct
Kill.
change in color. Now, if you were to take red and blue paint and mix them together, what color would you get, Ethan? We discussed this yesterday.
Green and purple.
Purple. Alright, is that a distinct color change?
Yes.
Alright, so think of it this way. If you were to mix red and blue together and you got green, would that be something to where you know that's not normal?
Yes.
Yes, so that's what it means by it says a distinct color change. Now, if you were to mix red and blue together, you would know they're mixing together, okay, I'm gonna get purple. If you were to mix together and get blue and get like green or white or clear, you know, that's not normal. That's a distinct color change. We're gonna see this in some of our reactions later on. They mix sometimes clear and yellow and we'll get magenta. That is an entirely different color, and it's depending on how they're chemically bonded and how they reflect light at that point. So that's what it means by a distinct color change. It's a not normal color change where you go, that's weird. That's not supposed to happen. Alright, anyone have any questions about these four that you need to know?
No.
No, ma'am?
No, ma'am.
Alright, separation of mixtures. How do we separate a mixture? Now remember, a mixture, is it chemically combined together or are they just next to each other? Chris? If it's a mixture?
No, they're next to each other.
Yeah, they're next to each other. So there's a couple different ways we can separate them out to where it's a little bit easier. The first one is kind of like boiling, but it's a more exact version of
Distilling.
boiling for it. Yeah, distillation. So for this one, I have a diagram. It might load fast enough for it, it might not. So just make a note for distillation. That for this one, this is whenever you have a homogeneous mixture or solution in a liquid form, it can be separated by distillation if the components have wildly different boiling point. Now remember, what's a homogeneous solution? What's that mean, Ethan?
It's the same.
All the way through without it. So if your book shows you a picture of it, I'll show it probably on Friday, maybe Monday. I'll show you the moving diagram for it. But basically they boil it so that way, if you have a substance that boils at a lower temperature, it'll go ahead and evaporate out and leave the other substance. Kind of like using salt water. Water will evaporate first before the salt pour. In some cases, if they have it to where the boiling points are really similar together, they have to use a special version of this called fractional distillation. That's what that picture's showing you on page 25. Basically, they stick little glass beads on the inside of it, and part of the gas gets stuck on it. The less volatile one, or the one that boils at the higher boiling point, it gets stuck and it can't get out. While the other one can go ahead and bypass. So they stick the beads to help slow it down, basically, and separate them out for it. So your book points out a similar process is used to separate petroleum. Anyone know what petroleum is?
Yeah.
Oil.
Oil specifically. And it turns into gasoline is what you were thinking of. So petroleum is separated into the various fractions. Alright, I'm gonna give your homework. Your homework for tonight is you're going to study, first of all, study. Also, you're going to read lab 4 and answer the pre-lab questions. Because of revival, we couldn't do lab 2 and 3 this week because it's too crazy for me. But read lab 4 and answer the pre-lab assignments. The pre-lab questions for lab 4, if you're looking in your lab book, it's on page 23. So read through the whole thing so that way you understand what's happening in the video tomorrow, but then answer the pre-lab questions.
Which ones?
All of them. There's only 5. It'll be okay. Alright, have a good day.